Welcome to two projects. In this video, we are going to see intrusion detection for cyber physical systems using generative adversarial networks in fog environment. Introduction. Cyber physical systems (CPS) need intrusion detection to defend against online threats. Machine learning algorithms can identify known attack class labels, but predicting and countering novel threats is difficult. In order to increase system resilience against monetary and operational disruptions, this project introduces an unsupervised intrusion detection system using generative adversarial networks (GANs) in a fog computing environment. Objective of the project. The project uses generative adversarial networks (GANs) in a fog computing environment for intrusion detection to increase the security of cyber physical systems (CPS). It involves using LSTM for time series data, developing a specialized FID-GAN for fog networks using a variety of datasets, offering a user-friendly interface and producing false positive rate graphs for system performance insights. It also involves developing an unsupervised GAN-based model for classifying regular and anomalous cyber traffic. By efficiently identifying both known and unidentified cyber attacks, the aim is to reduce monetary losses and service interruptions. Requirements. These are the requirements needed to execute this project. Hardware requirements: operating system of Windows, processor of i5 and above, RAM of 4 GB and above, hard disk of 20 GB and above. Software requirements needed are Python IDL of Python 3.7 version. These are the algorithms used in this project. The first algorithm is generative adversarial networks (GANs). GANs create fake data like an artist that looks like real data. They help our system learn tricky patterns in network behavior, enhancing detection of both known and new attacks. The second algorithm used is encoder model. The encoder understands and labels data, making our system sharp at telling normal from unusual activity, aiding in accurate intrusion detection. The next algorithm used is long short-term memory (LSTM). LSTM remembers patterns in time-based data, making our system adaptable to changing network behaviors, improving its real-time intrusion detection capabilities. To execute this project, we have designed the following modules. The first module is Upload NSL KDD dataset. This module involves bringing in a collection of network data that we will use to train our system about normal and unusual network behaviors. This module helps our system become smarter in spotting potential issues. The second module is Generate and Load FID-GAN model. Here, we set up a special system, FID-GAN, that learns by creating fake data and trying to trick itself. Think of it like a detective and a forger working against each other. This system is fine-tuned to work in foggy conditions, fog computing, and helps us identify unusual activities. The third module is Generate and Load Encoder model. In this module, we train another system encoder to understand patterns in data. It learns what is normal and what is not from the fake data created earlier. This understanding helps us figure out if the network is behaving strangely. The next module is Detect Intrusion from Test Data. In this module, we test our trained systems on new unseen data. FID-GAN makes more fake data and compares it with the new data, while the encoder tells us if it is normal or suspicious behavior. The last module is NSL KDD false positive rate graph. Here, we draw a graph that shows how often our system wrongly thinks normal things are suspicious, false positive rate. This helps us adjust our system to become smarter over time. By putting together these modules and using a special memory technique called LSTM to handle time-based data, we have built a smart system that can detect strange activities on a network and help keep it safe. Execution of the project. To execute this project, first we need to open the code folder. This is the dataset folder in which I have normal and problematic images. With these, we will train the algorithm. This is the model folder in which I have numpy, pickle and .h5 files. These files contain algorithm information. These files can be loaded into the project code during runtime to utilize the trained models. This is the NSL KDD dataset in which I have the dataset and test data. So in NSL KDD dataset, in the last column I have 0 and 1. 0 indicates normal and 1 indicates anomalous. So FIDGAN will get trained on this dataset and then predict attacks from unlabeled test data. Close this data, and this is the test data. So here I don't have the label column. This is unlabeled test data. GAN will take this data as input and then predict label from it. Close this, and these are Python main code files, and this is the run.bat file. Instead of executing the project in command line interface, we have created this Windows batch file. Double click on run.bat file. This graphical user interface will be opened. With this, we are interacting with the program. We have used Tkinter library to create this graphical user interface. Now click on Upload NSL KDD dataset button. A dialog box opens. Select the dataset and click on Open. So it confirms that the dataset is loaded, and these are top 5 rows of the data, and there are 42 columns in the data. Now click on Generate and load FIDGAN model. So it confirmed that the model is generated, and here we can see GAN generated latent generated point size 200, 32, 32 and 3, which describes that the GAN has produced a collection of 200 synthetic data points, each represented as a 32 by 32 pixel image. That means 32 height or normal or number of rows and 32 width or number of columns with 3 color channels. Now click on Generate and Load Encoder Model button to update GAN with encoder model for attack prediction on reconstructed data. So with FIDGAN we got 0.07 error rate. Now click on Detect Intrusion from Test Data button. A dialog box opens. Select the test data and click on Open. So here in square brackets we can see network traffic data, and after square bracket and arrow symbol we got predicted output as normal or anomaly. Similarly, GAN can generate fake data and then map or reconstruct with new data and then predict the label as normal or attack. Now click on NSLKDD false positive rate graph button. So in this graph, on x-axis I have false positive rate and on y-axis I have true positive rate. Close this graph, and in the text area we can see the area under the curve score. So with this we can see that the model is doing well. Close this, and in the console we can see the model building. The conclusion here is this project uses generative adversarial networks GANs in a fog computing context to present a reliable intrusion detection solution for cyber physical systems CPS. The cutting-edge FIDGAN model, which uses LSTM for time series data, demonstrates promising abilities in precisely classifying both well-known and undiscovered cyber threats. The project's potential to increase CPS resilience is further highlighted by the user-friendly interface and insightful performance evaluation. A thorough intrusion detection approach benefits from diverse datasets, FIDGAN's adaptability, and instructive false positive rate graphs.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.